Good afternoon. Thank you again for joining us for the Tulane Future of Energy Forum. It is my pleasure to introduce our next session, a keynote panel on Hydrogen Bayou, Louisiana's position as the next hydrogen hub. If time allows, at the end of the session, we will open it up for a few questions, but please take out your cell phones and we'll be showing a QR code on the screens. You can screen that QR code and submit any questions you may have. And again, if time allows, we will get to them. Other than that, please silence your cell phones. And at this time, I would like to ask you to join me in giving a warm welcome to our moderator, the Associate Director of the Tulane Energy Institute, Eric Smith.
All right, well, we're really glad you all came to hang around to this session. And Louisiana and hydrogen have both kind of flown under the observation deck, if you will, for a lot of people, but it's critically important to the economy of Louisiana, and we're one of the two states between Texas and Louisiana. We probably produce and use about 95% of the hydrogen that's produced in this country today, and it's all gray hydrogen, basically. To my left here, we've got Honorable John Bell Edwards, a graduate, proud graduate, we have to say, at West Point, 1988, right? That's right. And comes from a family on the North Shore around to Amite that's been involved with parish political activity and sheriff operations for generations, right? Yes, sir. And then beyond that is he was elected a state representative and served for a number of years in that role, and then of course went through 2 terms as governor of the state. During that time, he started a big effort run from the governor's office on industry decarbonization, recognizing that Louisiana without its petroleum industry wouldn't be the Louisiana we all know and love. So we're really pleased for him to come in and participate with us today. He's with a law firm here in New Orleans and elsewhere that's focused on some of these activities. Next to the governor is Leigh, and she is going to be representing sort of the new hydrogen, new ways to produce it, low carbon ways to produce it, or controlled carbon ways to produce it, and has a really interesting process to discuss. If you've ever heard of turquoise hydrogen, that's what she'll be talking about. She's been a reporter, has worked out at NASA as part of the whole space program that was going on out there, and I'll let her describe more of that, but she also served as the Southeast Louisiana Regional Director of the Coastal Conservation Association. Originally has a BA from Syracuse in broadcast digital journalism, and then a master's in Homeland Security and emergency response management from Tulane, so an alum. And then finally, we have James Donahue. Jim is the professor of chemistry, focusing on inorganic chemistry and some of the catalysis that goes on in that area. Tulane's very strong when it comes to catalysis. That's something most people can't spell, much less do. But it's basically how do you facilitate chemical reactions by introducing materials that are constantly renewed so that you are able to reduce the pressure, the temperature, or the electrical input necessary to run these processes. So without further ado, I'm going to let the governor kick off and say a few words.
Thank you, Eric, and thank all of you for being here this afternoon. You know, this is an extremely important topic, and I will tell you that I believe, and even though we were unsuccessful with our HALO initiative, Hydrogen, Arkansas, Louisiana, and Oklahoma, that Louisiana was and is a de facto hydrogen hub. And if you just look at the role that we play and have played with respect to hydrogen in the United States and in the world. I think that bears it out. So as governor, you all may be aware that we had a climate action plan that was developed, and we really promoted the energy transition, and by embracing it, understanding the need to reduce CO2 emissions. And Louisiana is unlike all the other states. We're the only state where the majority of our CO2 emissions don't come from power generation. They come from refining and petrochemical manufacturing. So our solutions have to be a little different. We focused on electrification of industrial processes. As much of that electrification needs to be renewable and or just non-emitting as possible. You have to do carbon capture, sequestration, and use hydrogen as a fuel source whenever you can. And of course, there were other strategies and action items as well. But Louisiana is ideally suited and situated for these hydrogen efforts. And again, I think we are a de facto hub. And you just look at the natural gas, it's priced at the Henry Hub in Erath, Louisiana for a reason. And most of the hydrogen, Eric mentioned this, is gray hydrogen today. And we know that you can, at scale and economically, produce hydrogen that way. And there are no technology risks and so forth. And then if you put carbon capture sequestration either on existing or new facilities that use the steam methane reforming method for producing hydrogen, then you get blue hydrogen. And so that is obviously the easiest, cheapest, least risky way to produce large amounts of hydrogen at scale. Louisiana is situated ideally for that because obviously we've already been doing that. And I'm going to show you a few slides. But when it comes to carbon capture and sequestration, we have the pipeline density to move the CO2. We have the geologic formations to safely and permanently store it. And so we really have tremendous advantages here in Louisiana. And I just want to, they say a picture's worth 1,000 words. I'm going to run through some stuff pretty quickly here. But you see what the North American demand is currently? It's 10x that if you look at planned and potential demand. But look down at Louisiana and Texas, the Gulf Coast. You see the red there. That sort of shows you how we're already positioned. And then with respect to the Gulf Coast, currently 42% of the demand is Texas and Louisiana. 74% of the planned demand. And of course, the planned is much more concrete than what is potential. But you can just see going forward how much of this is going to be in Louisiana. This is what it looks like in terms of current and planned and potential, and with methanol, ammonia, semiconductors. And ammonia is huge because we're always going to need ammonia for fertilizer here and around the world. But secondly, I think you all know this, ammonia is a principal way to actually export hydrogen. You get it where it's going. There's over 100 ports around the world that have been dealing with ammonia imports for a long time, so it's not new. You crack it back into hydrogen, you have an energy source. And you're seeing a lot of foreign investment in Louisiana to do just that, and especially coming from places like Japan, where they're also buying our natural gas. And I'm kind of excited that I think they're going to be generating power using natural gas that comes from Louisiana, augmented by hydrogen to reduce the carbon footprint of that power generation, and the hydrogen is going to come from Louisiana. You look at the current supply, and you see down in Texas and Louisiana where what that looks like, and then this is planned, and you see those two big dots, Louisiana and Texas, and that's why I say we are already a hydrogen hub, despite the fact that we didn't get one of the awards that was made. And then you see the Gulf Coast supply there, Louisiana and Texas, 60% of the supply currently of hydrogen, and then 25% of what's planned. And so I just wanted to show that, and these are just because a lot of these brands you're familiar with, they're all playing in Louisiana right now in hydrogen, every one of them. And so I just wanted you to be aware of that too. And for the sake of time, I'm going to skip the supplemental slides. And by the way, in a few minutes when you start asking questions, just understand these other panelists are really experts. You might want to direct your questions to them. But if you do direct one to me, I will do my dead level best to give you the right answer. But thank you all so much. Appreciate you.
Hi, everyone. We're just waiting for the slides to come up. But again, I'm Leigh D'Angelo. I'm kind of representing here, like you said, a new hydrogen opportunity. So you heard the color terms gray hydrogen and blue hydrogen so far, using methane to create hydrogen in different ways with different types of carbon capture. What I do with modern hydrogen is we capture that carbon before it's combusted. We don't create CO2 that you have to then go and store or use energy to transport afterwards. And so I'm going to run through very quickly, if I can, what modern hydrogen does, how our technology works, and how this is an opportunity, especially in a place like Louisiana, who has politicians who have already been pushing the hydrogen economy for years ahead of the rest of the country. So technologies like this are much more understood and appreciated in places because of your work you've been doing for years already. So again, quick company background. Modern Hydrogen is technically a startup. We've raised $100 million from Bill Gates himself, which is pictured here, but importantly also from utilities, who are also our customers. So National Grid and NextEra are some of our investors, and our customers include Northwest Natural in Portland, Oregon. This is what a lot of people don't understand when they're thinking about emissions. You hear things like electrify everything, and they can see solar panels, they can see wind, they understand the opportunity to decarbonize electricity. But 40% of emissions come from heating, and it is much harder and much more energy intensive for those industries to switch over to electricity. Not only would it be entirely new workforces, but it would be entirely new operations, shutting down your operations to make that conversion. And so we know that generating high temperature heat from electricity really doesn't work with today's technologies. And so we need a high heat application that's faster and more effective for decarbonization. I'm sure you've been hearing this over the past few days, but the demand is not going to stay flat. We are going to see more demand for energy in general, and especially on our grids, of course, and our grids are not going to be able to keep up with that demand. So looking for additional ways to incorporate hydrogen into the decarbonization strategy means that we'll be able to relieve some of that demand pressure on the grid. So what do we do about heat? As you can guess from the name of my company, Modern Hydrogen, we suggest hydrogen. Electrification can't solve the issue, so we need that heating fuel that doesn't release CO2 or other greenhouse gases. And to your point, we have a lot of gas infrastructure nationwide, about 3 million miles of it. And CH4, that methane that travels through the natural gas lines, is 80% hydrogen atoms. So just as you were saying, ammonia can act as a transport, so our natural gas already does. And it moves a lot. We're talking about the size of gas use being coal plus nuclear plus solar plus wind plus hydro combined today. So we're using a lot of gas, and it's moving across the country already. And if you don't remember anything else that I say, remember this animation here. What we're looking to do that's different than the blue and gray hydrogen for massive scale uses is really make it scalable for individual industries. So if you see here, you've got the natural gas coming in on the left, going to the manufacturing facility, and then those are our boxes. We call them the MH500. They produce about half a ton of hydrogen a day. and they're scalable. So if you want to start by decarbonizing one boiler, one furnace, you can do that with our technology, and it's modular, so you can grow from there. And you can see that that hydrogen is then used for feedstock, process gas, your furnace, your boiler, power generation, and we also work with the hydrogen heavy transport industry and fleet fuel. So bottom line, why do we like turquoise hydrogen? You don't need new infrastructure. You don't have to worry about transporting hydrogen or storing your hydrogen. We also don't have to capture CO2 because we don't create CO2. We are taking the carbon out before it's combusted. It looks like a black powdered sugar. It's an actual solid form of carbon that we then use as a value add in asphalt products. So not only are we creating hydrogen, which is a clean fuel to use right away for those industries, but we're taking that carbon and also using it. We're not storing it. We're not using energy to hide it underground, although Louisiana does that very well. We're actually taking it to improve our roads and decarbonize our roads in the process. And we don't use electricity for our process. We power Modern Hydrogen's units with a portion of the hydrogen we create. Why behind the meter? You're not constrained by the electrical grid. Like we said, we're all about creating value. I think a lot of our conversation today is going to be how do we further the hydrogen economy when you've got what seems to be competing conversations around maintaining industry and decarbonization and climate goals. When you're creating value, you're doing both of those things. You are able to leverage your existing workforce or expand it and extend the useful life of existing infrastructure. So really bolstering existing American infrastructure and pipelines by making sure we use our existing infrastructure. I will run through these very quickly for those interested on the technical side. This is what our technology mostly does. It's not what it looks like, but it's basically a filter. So picture the natural gas coming into your home, for example. This is not for home use, but just so you can picture, right before you turn that stove on, we would have our product right there. So it's sitting right there, and you don't have to worry about transporting or storing that hydrogen. And then again, we take that solid carbon away. So we do have a small carbon footprint at the very beginning. We use your existing natural gas line to heat up our pyrolysis chamber. So picture a little bit going into the combustion zone for a few hours. We heat up that combustion zone to bring our pyrolysis chamber to temperature. And as we do that, we are sending our methane through the pyrolysis chamber, which is then creating both hydrogen and solid carbon. Again, we use a portion of that hydrogen at that point into the combustion zone, and we stop burning CO2. So for hundreds of hours, we're burning hydrogen instead of carbon, instead of CO2, creating CO2. And we've got our solid carbon that comes out here. This is a much prettier way of looking at that. You can see the methane coming in on the left, the carbon falling out at the bottom. Again, it kind of looks like falling black snow, and a portion of that hydrogen going back up that we use for combustion to create hydrogen. This will be my last slide, I promise. This is a big deal for our industrial and utility customers. We have two examples, one in Portland, like I said, with Northwest Natural. We've passed all safety, reliability, quality aspects there, and they are using it as a blending project. So they are taking some of the carbon out and putting our hydrogen back into their pipelines for everyone. In Miami, we passed all of our requirements there, and they are using it for zero CO2 power generation, looking at using hydrogen for peak shaving opportunities. So thank you for listening to me and going through my slides, but really excited to be here.
Thank you very much. Well, now, Jim's going to give us a few ideas as well, and then talk about the magic of catalysis, I hope.
Okay, thank you, Eric. I'm not sure if my slides are up yet. Okay, there we go. I wasn't sure how familiar these color descriptors would be to everyone here, so I prepared a slide here that would explain the meanings. So brown hydrogen is not a term I think I've heard today, but it refers to hydrogen that originates from coal via a gasification process. And I think the usefulness of these color descriptors is that they evoke sort of the environmental friendliness in degrees. So brown is not a color you would imagine as being environmentally friendly. Gray hydrogen, which we have heard about, is a hydrogen that originates from the steam reforming of methane, and it's superior because it has a hydrogen to carbon dioxide ratio that's twice as high. Therefore, the carbon footprint is lower. Next is the blue hydrogen, which is very similar to the gray, but differs in that the CO2 generated is sequestered and stored. And then we have the turquoise hydrogen just mentioned, which is even better still because it doesn't generate any CO2. It's a pyrolytic method that doesn't leave the CO, or the carbon rather as CO2, but rather is just elemental carbon, just graphite, which is useful for other things, as Leigh mentioned. And then finally, we have what is referred to as green hydrogen. And this is sort of the space in which my group and some of the other groups across the way here in science and engineering work. So we are trying to devise ways to use renewable energy inputs to split water and thereby create hydrogen and elemental oxygen using either photoelectrocatalytic or electrocatalytic means. So I want to say a few words about relative costs because this is very germane to the practical realities that we have to really come to terms with. So these slides here are these equations here are chemical, and they give you some appreciation for the words I just mentioned, namely that steam reforming, if you couple it with the following reaction, water-gas shift reaction, that generates for every molecule, or every atom rather, of carbon, 4 equivalents of dihydrogen, whereas coal gasification is only 2. So consequently, it's better. And the pyrolytic decomposition of methane to make graphite, well, there's no CO2 involved, so that's even better. In this graph here at the bottom right, what you, if you can see it, appreciate from the bottom right is that, well, coal gasification is the least expensive, and therefore it's still widely used in other parts of the world, especially China. But when you couple it to carbon capture technologies, the additional cost is actually surprisingly moderate. And so that reality means that for the foreseeable future, these technologies of steam reforming of methane with carbon capture and turquoise hydrogen, these are going to be our primary ways of making hydrogen. Now, you may not be able to see it, but there's a tiny gray sliver in both of these pie charts, which represents the formation of hydrogen by electrolysis. And it would be my desire and my hope professionally to make that little wedge a bit bigger and so make hydrogen by green methods not just a niche production, but rather something more substantial. So before I say a little bit about some of the things we're doing, I want to emphasize why it is that me personally, I got into this area, and it's because hydrogen is going to be necessary no matter how you look at it. You don't even have to talk about using it as a clean energy fuel. You have it as an essential ingredient for so many other processes. So ammonia production was mentioned. So ammonia is produced in prodigious quantities. I think it's 183 million metric tons per annum or thereabouts. Mind-boggling amount, primarily for agriculture, but for other uses as well. Hydrotreating of petroleum feedstocks. It's the largest process industrially in the world by a considerable margin. There's something to the tune of 103 million barrels of oil processed every day throughout the world. That's hard to comprehend how large of an amount that is. But we can't just burn crude petroleum. It has to be processed. It's loaded with, well, depending on the source, differing amounts of sulfur and nitrogen, and those atoms have to be removed to the extent possible by this hydrotreating process, which removes, as you can see from those equations, the sulfur in the form of hydrogen sulfide and the nitrogen in the form of ammonia. And if you don't do that, well, they end up as oxides of sulfur and oxides of nitrogen, which lead to acid rain and smog. So we have to have this hydrotreating process. But not only that, there's lots of other processes that attend the refining process, and many of them use precious metal catalysts that would be absolutely killed by sulfur in particular. So that's another reason to get rid of it. Another use for hydrogen, olefin hydrogenation, that's particularly important in the food industry. Increasingly, hydrogen is used for the reduction of metal oxides to create the metal. That's an alternative to the use of carbon monoxide or coal. And then, of course, you have its use as a clean energy. So even if you don't want to talk about the clean fuel, you've got all these other applications and many more besides that make it relevant and essential. The image I like to use when I talk about hydrogen is that it's the flour in your kitchen. It's the ingredient you need just about every time you go and start thinking about baking something. You need it. So we, for that reason, decided to start to work on catalysts that mediate the formation of hydrogen from water. And this scheme here may not make a whole lot of sense to you, but the essence of it is that one is using an electrical potential to drive electrons toward one electrode compartment that's separated from another by a membrane through which protons can pass. And so you use that energy input to drive the splitting of water, and so electrons combine with protons to make dihydrogen, and on the other side, you have water being oxidized to oxygen. And that's the overall equation. And what you have to appreciate is that that's energetically uphill. It has to be, because what you're making is something that is a fuel, hydrogen. If it wasn't energetically uphill, it would have no use as a fuel. Okay, you have stored chemical energy in the form of that hydrogen-hydrogen bond. But that's not the problem. The problem is that what lies between is something called a kinetic barrier. You have to overcome this little mountain. You have to traverse over it to get to your final point, which is a little bit lower in energy. And so that kinetic barrier, which is also referred to as an overpotential, if you're doing this electrolytically, that's wasted energy. And so you want to somehow make that barrier as low as possible. And that's why you want catalysts. So these parallel vertical electrodes you see in the water, they could be functionalized with some small molecule catalyst on their surfaces that actually just changes the way the reaction is being done. It provides a totally different pathway. So you might imagine it as boring a hole through that, or a tunnel through that little mountain, and making the passage from one side to the other easier. And so lots of things can be used as catalysts. The problem is scalability, cost, lifetime. And I would contend that one of the few, maybe the only material that is scalable is plain old molybdenum sulfide, which has been known to the ancients. It's been known for thousands of years. And it looks like graphite, that grayish material you see in the picture, and it has a graphite-like structure, very planar sheets. Anyway, what we decided to do in my lab, and have been doing for several years now, is making small molecules that are fragments of that extended planar structure, because the real business part of it is the edges and any defects that you can create within or on top of the plane. So, to make a long story short, well, molybdenum sulfide has maybe 1/1000th of the cost, but about 1/50th of the activity of the ideal catalyst, which is platinum. So therefore, it's got the mathematics on its side. So these are images of some of the clusters, small molybdenum sulfide or molybdenum selenide clusters that we can make. These are actually experimentally determined structures using techniques called X-ray crystallography. So we can make and control with a very high specificity quite a wide range of clusters, and they differ in their activity. And so we're teasing out composition function or composition activity level relationships in my lab now. And with my senior colleague, Russ Schmel, who may be in the room here perhaps, we've been using primarily a photolysis system to assess these activities. So I won't get into the nuts and bolts of it because it's not really that important, but we're using light as an energy input, and then we use electrons from a sacrificial donor to channel electrons to our catalyst, which is illustrated as that little sphere at the bottom. So that's, I think, all I have to say. So I'll just end with that, and be happy to field any questions if there are any.
Well, there'll certainly be some. We're going to go through a couple of quick ones here, and we'll just alternate. Anybody who wants to pitch in is
I thought
welcome
we
to
were
do
going
it.
to give them a quiz on that last presentation first.
No, well, just you. That's the way that works. We talked a lot so far about producing hydrogen and the benefits of hydrogen, but one of the major commercial issues is transporting and storing hydrogen. And hydrogen's the smallest molecule we have. It'll literally bleed through you and I, but it'll bleed through steel. It doesn't have any faults. It's just a very small molecule, and steel's not so small, so it'll work its way through. So it's not really easy to contain. And then, of course, when you start trying to get energy density, you start compressing it, it's even harder to contain. So, Jim, starting with you, what have we seen happen? Oh, the other point I would make is we don't usually build hydrogen plants next door to the consumer. We build them, maybe an ocean away, and we've got to get the hydrogen delivered. We can use some different approaches to do that, but what do you see in the lab that might be promising for that sort of an application?
Well, for the particular issue of storage, which is a really big issue, I know that in recent years there's materials of a type called metal organic frameworks, which are very light and very porous materials into which the gas can diffuse and then be extracted. There's been a lot of debate about whether those are ultimately going to be cost effective, and I think there's a consensus, to the best of my knowledge, that they may not be. But it's not a simple problem to solve for sure. So in addition to the diffusion of hydrogen through materials, a particular problem that it causes with metals is embrittlement.
Right.
And that, of course, would lead to failures if you're talking about pressurizing as well. But so to the best of my knowledge, the way that is dealt with is by blending hydrogen with other gases like methane, and then on the other end of a pipeline, it can be separated.
I know we proposed to Entergy at one point that they go to one of the gas plants at Waterford, because conveniently the hydrogen pipeline that we do have runs right past the front of that plant, so that they could set up a trial without too much complication to see what level of blending you could do. I think most people would agree 10 to 20% will work, but you get much above that and you start getting into the kind of problems you were talking about.
Yeah, that's exactly what our customers are seeing as well. So the Northwest Natural plant where we have our unit does, like I said, some blending, and they're expecting to be able to go up to 20%. That's not our technology demonstration we're doing with them right now. And like you said, a lot of hydrogen plants are very far away. We are tackling that issue by saying, let's bring them on site, so you don't have to handle that transportation or storage, not only for, in my very non-technical term, I just call hydrogen slippery. It makes it out through all sorts of different ways of transporting it. But think about the energy intensity you have of transporting it by truck. If you're really moving your clean fuel to you by a diesel truck, then what are you doing? And that's a lot of the ways that people are getting their hydrogen now. Even with green hydrogen, if it's not on site, you have to think about how you're getting that hydrogen to you. So that's why we said, let's just go to the very end and see if we can solve that by putting it on site.
Governor, you're sitting here. I know you don't want to critique your predecessor or your follower, but the issue is, what do you see state governments doing really across the board in terms of trying to facilitate this portion of the transition?
Yeah, so obviously different politicians, elected leaders, and certainly of different parties have different ideas about whether climate change is real, whether we need to be doing any or all of this. But everybody who is in elective office is interested in economic development, investment, job creation. And so we tend to promote that which is going to draw investment and diversification of the economy and create jobs. And so I think you're going to continue, even when you hear people talk differently about the climate and about the energy transition, and quite frankly, my successor and I see the world very differently, and we talk about it very differently, but at the same time, he hasn't done anything that would curtail the investments that have started to come to Louisiana because of what I just said. So I think that that's likely to continue. And quite frankly, we've been an energy state for over 100 years. If we're an energy state 30 years from now, it will be because we embrace this transition. And so that's going to be incredibly important for us. And I think that in the short term at least, the easiest way to transport hydrogen is the way we've been transporting hydrogen, and that is as ammonia. You know, there's a lot of comfort with that. We have vessels that do it. We have ports that are equipped to handle that. It gets where it's going, and then you turn it back into hydrogen using one of those processes that that's been explained to you already. So I don't see these things as insurmountable, but this is a transition, and the easiest thing to do now is that we're already doing as we try to bring on other alternatives and get the cost down so that we can do them at scale. And I think Leigh is right, to the extent that you can do this without ever creating the CO2 in the first place, I think we're all better off. I think that if we can get to green hydrogen, if you can make hydrogen out of water using renewable electricity, that is obviously ideal. You burn the hydrogen and your byproduct happens to be water again. That too is ideal. But we're not ready to do that at scale today. And so we're going to have to do in the short term that which we have been doing, and then just put the carbon capture sequestration on top of it as time plays out and these other things come to fruition.
Okay. While we're on that general subject, let's talk about transportation. One of the things that's in at least the technical papers these days, people like UOP, Honeywell have been big promoters of it, and we actually do some of it at one of the refineries here locally, out here in Chalmette. We're making renewable diesel and using a hydrogenation process to do that, and actually using an old hydrodesulfurization unit to sort of implant the hydrogen, saturate these vegetable and animal fats with the hydrogen, and we call these liquid organic hydrogen carriers. Ammonia is one of them. So the theory is you can take a chemical that's an item of commerce today, something like toluene, you can hydrogenate it, make a cyclohexane molecule, which there are 1,000 ships that can move it around. Pipelines can move it around. It's just a standard product, if you will, intermediate. You get it to the other end, and you dehydrogenate it. So we've got catalysts to do, this all takes place at high pressures and pretty elevated temperatures and stuff. But basically, we're able to handle the transportation step and the storage step using existing equipment. Do you see any shortfalls, if you will, in using these organic carrier type cyclic molecules?
I guess it's sort of a relative advantage issue. I mean, you still have an energy expense if you're going to reduce a molecule like toluene to methyl cyclohexane and then back, but that's less than what you'd spend, doing the transport some other way. That's really what it boils down to.
That's my point. I mean,
Yeah.
The first thing that comes to people's mind, just use an LNG ship. Well, it's colder than LNG, if you can imagine that.
Right.
And LNG is minus 260 Fahrenheit, so it's cold enough to break steel just by itself.
And I think there's a real safety advantage to doing it that way as well. So hydrogen is a very fickle molecule, extremely touchy and combustible and ignitable in very small proportions with air. And so when you additionally compress it to a high-density gas or even to a liquid, it's fraught with even more risk. But you sidestep all of that if you do what Eric was just saying. You reduce some organic molecule in a reversible way, and then on the other side, at the place to which you're taking it, you undo it that way. So much safer. So.
Well, I think that's one that we really haven't done, but it's we're not going to be able to sell renewable diesel to California for life. It's going to be something that gets done in California, at which point either the rest of the country is going to be consuming it or we're going to have to come up with a plan B. Fortunately, this kind of a process will work whether you want to make diesel or jet fuel or gasoline. We already have the chemistry in place for alkylation and for esterification of these molecules. So I think that's one that has a lot of promise. And at the end of the day, we can do a bang-up job producing the chemistry, but if we can't deliver it to somebody that can consume it, we've wasted our effort. So it's got to be viable on a delivered basis. Governor, you have any issues with that? Or?
That discussion, generally speaking, was well above my head.
I'm sorry.
But I can say, generally speaking, what we're seeing is a lot of projects that started off several years ago as renewable diesel projects have been converting to sustainable aviation fuel projects. And the production process is very similar. The feedstocks are very similar. It's just the market analysis of that. And so renewable diesel, you're depending largely on RINs, which are very volatile, but also on very substantial state tax credits, which may or may not exist in that amount or however many years from now. And so there's a lot of uncertainty on that side. There's a lot more certainty around sustainable aviation fuel. So you are seeing a movement away from new projects on the renewable diesel going to sustainable aviation fuel. So for example, in Japan, they're mandating that their airlines use sustainable aviation fuel in certain amounts that are going to increase over the years. And then you can actually get incentives here to produce it. And so there just seems to be a lot more momentum around that as opposed to the diesel. But the rest of that conversation, by the way, I did pass an organic chemistry at one class at one time in my life, but that was not yesterday.
Okay. Me too. Take another step. Leigh talked a little bit about the alternate uses of hydrogen. Let's go ahead 10, 20 years, and we've got, this hydrogen available in a form other than gray hydrogen. It may be blue, it may be green, but turquoise. But now that we've got it, is it better to use it as a fuel or is it better to use it as a chemical feedstock, economically or practically?
Yeah, I think, won't that depend on what the cost of that hydrogen is relative to other things that could be used? So for example, I know that there are new natural gas power plants that are being built in this country and elsewhere today that initially are going to use 100% natural gas, but they're going to be capable of using up to 50% hydrogen. Whether they ever burn hydrogen will depend on how much that hydrogen costs.
Yes.
And so I think the cost of it is going to make, or on the other side, are there going to be incentives to offset and increased cost that still makes it worthwhile? Or do you have customers who are willing to pay a surcharge? And I think a lot of the energy transition, decarbonization was kind of premised on this idea that the lowest carbon footprint hydrogen might fetch a premium. There is very little evidence to support that that's going to happen. The market typically buys whatever it can buy at the cheapest. And so that's, I think price is going to be determinative of a lot of that.
Leigh, you're sitting there with the same issue. You pointed out 5 or 6 different applications. Do you have any sort of a ranking of those in terms of your preferences?
Yeah, I do. And you started the question off by looking ahead 20 years. If we work backwards from that, the infrastructure that has to be starting to go in place, the permitting reform that has to happen so that infrastructure can start to go in place, all has to start happening today for us to be able to get to a point to even be able to answer that question. So if we had the hydrogen today and all of that went great, you have to make sure that you're using your renewable electricity first in the most efficient way. We're not suggesting you use hydrogen for heating your homes when you've got electric heat pumps that can do the job. We are suggesting you use hydrogen for fuel in places where converting to renewable electricity would be cost prohibitive. And so for us, the first few customers that we're working with are looking at heavy industry. So anywhere where you're using a lot of heat or steam, think bottle making, for example. You picture those big hot boilers and furnaces. That's an initial place where we think it makes the most sense. And then also we're working a lot with fleet fueling for heavy trucks. Where electrifying those heavy trucks make them obviously extraordinarily heavy, and they've got too much downtime when you have those big batteries on them, and they're looking for other alternatives, and we think hydrogen's another great place for that.
Okay. Jim, you're sitting over there with a smile on your face. What do you see in terms of the relative purity of these various hydrogen sources? And I know fuel cells that run on hydrogen need 99.999% pure hydrogen to keep from fouling and destroying their anodes and cathodes. How do we get there? And what's kind of the roughest purity that we can use, say, in a Rankine cycle power plant, and then what's the most purified version we need for some of these applications?
Okay, so for use as a fuel, I don't think the hydrogen has to be particularly clean. It's been used for eons, well, not eons, for many decades, if not more than 100 years, as syngas, which is just sort of a variable mixture of carbon monoxide, hydrogen, methane, and other things. And in various proportions with these other things, it can still burn and be used as a fuel. So I don't think its use that way is particularly sensitive. But to other things, like in the semiconductor industry, you really need to have ultra-high purity methane to sort of cap the surfaces and edges of the silicon wafers and things like that. So it's very, particular to the application. But one thing I'm inclined to add to the conversation here is that there's a number of wild cards here to the larger picture. And one might be, for example, some breakthrough that we haven't mentioned, which is nuclear fusion. If that actually became viable, energy would be so inexpensive that all the considerations we're talking about now become irrelevant. Or maybe the technological breakthrough to recycle carbon dioxide directly and use it as a carbon starting point. Again, that might make other chemical fuels more viable, like methanol, which has lots of advantages because it's a liquid at standard temperature and pressure. It's sensitive to or subject to all these other problems. And so, some of these things could be, 30 years down the road, realities. So that would change the complexion of the situation quite a bit.
do you see, and anybody can answer this one, but do you see a role for the national labs in any of these sort of partnerships? We don't have a national lab, neither does Texas, and that's probably a glaring error by somebody, but the national labs have sort of taken over that primary research function and at least applications type work. And do you see partnerships with them being a contributor?
Yes, so the national labs are under the administration of the Department of Energy, and they do have a lot of things, but basic science research, including fusion research, is one of them, but they also do a broad array of science that's very chemistry oriented as well. And so yes, we have opportunities to work with them and get certain kinds of measurements and experiments done if we want to do that. But yeah, they're very, very good. They're very well equipped, and they're very willing to work with academic scientists, and I think people in private business as well.
From the private business perspective, I can announce as of yesterday, Modern Hydrogen was just awarded a DOE voucher funding for our life cycle analysis for the carbon itself that comes out. And so working with the various DOE departments set up to be focused on decarbonization, we're trying to take advantage of that, as are our customers, as much as possible.
Well, Governor, when we talk about these national lab partnerships, do you see any difficulty with the IRA or any of the federal funding that's been focused on applications in Louisiana or in Texas, working with a national lab that's not here, because we don't have one?
We don't. I was fortunate recently to be in Boulder, Colorado, and I went to one of the labs that actually is working on energy, and they had solar, wind, and hydrogen there, and they're doing it in partnership with private industry, I can tell you, and they're doing some really great work. I think the Inflation Reduction Act, to the extent that formal rules, final rules, I should say, haven't been promulgated and funding hasn't been allocated and so forth. After the election last week, there's a lot of uncertainty around that. And I don't know exactly how that's going to play out. And anybody who tells you they know exactly, they might be right, but they would be lucky. What I can tell you is I think that's going to benefit those people who had already started, for example, under the 45Q. They're not waiting for the 45V. The 45Q is the tax credit that helps with the carbon sequestration. We actually had some very big projects in Louisiana that reached final investment decision when the 45Q was valued at $45 a ton. It's now $85 a ton. And so you're going to see that, and Air Products, for example, $4.5 billion investment in Ascension Parish to produce hydrogen, blue ammonia, but it reached final investment decision under the older 45Q. It's now got the enhanced 45Q. And so I think that side of things are going to continue to move without a problem, because that's not something that is really uncertain. I'm not sure, and I hate to say this because I think it's really important that we not lose a moment in developing green hydrogen, but I think you're going to see a lot more uncertainty around that, because so much of that was focused on the 45V and trying to get the $3 per kilogram of production tax credit, the maximum amount that you could get. And we just don't know, but hopefully that program will develop, and those production tax credits are going to be there, and they will go back pretty quickly and create the certainty that is needed to get the investments going. My fear is in the short term, you're going to start seeing projects that have been announced being suspended, and we just can't afford that. We have to have a sense of urgency about this energy transition.
Well, that sounds good. We've got about 5 minutes to go. Do we have any questions from the audience?
We have lots of great questions. Why don't we start with this one? You've touched on this a little bit, but are there emerging technologies that can help repurpose existing infrastructure like gas pipelines to make hydrogen more efficient and cost effective?
I'll start, and anybody else can pitch in. I'd say the short answer is yes. I tried to outline one of those, which would involve using existing hydrogen pipelines and on-site blending to test out the use of hydrogen blends as a fuel. We probably should be thinking about the same sort of thing for ammonia and for other products. In fact, CF Industries here in Louisiana, incidentally, the biggest ammonia plant in the world,
Yep.
is building an electrolytic system to introduce the use of green hydrogen. It'll be tiny compared to what they're using on the methane side, but the ammonia doesn't care. You know, the hydrogen is the same regardless of what color we call it, but that's a promising development. Another one that people have talked about is using nukes if they start up again, and we have small modular reactors. That's a way to get the heat and electricity that you need to sort of supplement the wind and solar that you might not have enough of to produce hydrogen. You're going to be arguing with the folks who want to use it all for data centers and LNG export terminals, but the fact of the matter is nukes are sort of going into a renaissance as well. So yes, there are systems with a lot of promise. Right now, the world's got or at least the U.S. has got maybe 2 extended hydrogen transport systems in place. One of them's about 50 years old. It starts out at Jackson, Mississippi, and ends up in Houston. The Green Line, which was Air Products system. So.
I'll jump in and say, of course, you've heard from me on this that our main value proposition is that you could use the existing natural gas infrastructure to create hydrogen at the end of the line. But what I really want to add is when you think about existing infrastructure, it's not just the pipes, but it's the workforce. And so maintaining the jobs that are already here without having to go through massive amounts of new training and be able to expand on what we are already best at is an important part of that maintaining the existing infrastructure conversation as well.
That's true.
Yeah, and I don't know if you showed it on the colors of hydrogen, but when you use nuclear power to split the water, is that pink?
That's pink.
Is that pink?
Yeah, and then
So-
there's geologic hydrogen.
So, I mean, using existing infrastructure, around the country now, they are looking at decommissioned nuclear reactors, including 3 Mile Island, by the way, but not the reactor that had the problem. They had another one, and they're going to put that back into service. And so, to the extent that, because it's so expensive and takes so long to build one from scratch, that they're going back to ones that were decommissioned because they got where they just weren't cost competitive, but now they are again. And to the extent that that's used to power the process of splitting that water into hydrogen and oxygen, I think that is an answer to the question as well.
I think there's also the moral issue that we have to face. People don't like to face moral issues generally, but one of the issues when we talk about ammonia, you've heard some of the earlier speakers in the conference talk about there are things that we want to have and there are things that we need to have. And one of the things we need to have is a viable ammonia business, or else half the world's population goes away. And then you're in the position of saying which half. And people might have different opinions on that. So, do we have any other questions? One more.
We can end on a question for Jim. How close is the molybdenum sulfide process to market scalability?
Oh, that's a question I get from time to time, and I would have to say it's a period of years at the very least, many years actually. We're starting to come to a pretty detailed understanding of how molybdenum sulfide works, and I think one of the things we've learned is that it's a very forgiving material. It's got a number of modes of catalysis that are viable, and it can go, it's kind of like a spider's web of pathways that it can go through, some involving the metal and sulfur, some involving only sulfur, and so it doesn't really matter, I think, how pure or how cleverly you nanostructure the material and so on and so forth, it'll find a way to get it done. But the issue is, scalability. How do you functionalize it onto some surface, let's say, an electrode, one side from which you deliver electrons, and then the other side from which you get water. Those are technically rather challenging because you have to have some sort of way of chemically tethering the cluster to the surface, and we've been struggling with that particular issue for several years without really turning the corner on it. And then you have issues of catalyst deterioration, and so even though it's not especially expensive, if your catalyst will peter out after 10 to the 3 or 10 to the 4 turnovers, well, that's no good. You need to get around 10 to the 9, 10 to the 10 turnovers before you really start to make an impact. So lifetime, feasibility of making it in the laboratory and minimal steps, robustness in terms of how well it stays to a surface. All these things are, the distinctive problems, but I don't think we're going to be near to, market offering anytime soon, unfortunately. But I do really believe that molybdenum sulfide is where I see a future, no matter what. It's been used, I'll come back around to some of the chemistry I mentioned earlier. So the hydrotreating process used for petroleum refining, it uses hydrogen as an input, and molybdenum sulfide is the activator there. It sort of facilitates the breaking of hydrogen and the reduction of the organic material. And that's exactly why it's a catalyst. It can go the other way as well. It just mediates bond breaking and formation quite easily. And so if it's good for petroleum reduction, it's good for hydrogen formation as well. So that's where I would put my money if I had the money to put molybdenum sulfide and materials like that.
Well, since we're out of time, I think that was a good way to end, is just bring money. All right, let's thank our panelists for participating.